Okay, yeah, it's recording now.
Who wants to go first? We could take turns, little 5-minute snippets or something which could develop into bigger conversations.
Just one quick thing. I kind of like the, history of science and how people eventually reach these ideas. And, you, Hoshin and Pravin and, Jasper's here now too, have tons of experience in hydrology. And I'm kind of curious how, like, what steps and decisions led you to information theory being important. I know in the 80s, 90s, thousands, you guys were working a lot on uh, optimization, and now that seems to be a little bit less in the limelight. Yeah, so I'm curious
Hmm.
about that.
By the way, Joe, do you have access to video? Because I was trying to figure out who was talking and I couldn't,
Yeah.
couldn't see any lips moving. That's great. Thank you. Praveen, you want to take that one?
I can tell you my journey, and which is probably different from anybody else. I have been historically interested from the time I started as an assistant professor of 30 years ago in complex systems. And what that essentially means is how do pieces interact to create something new and different, which each individual piece would not uh, manifest. And so sometime in the 90s, I started looking more and more into complex system dynamics and as the field was evolving. And I was at a NASA meeting at NASA, and I'm guessing it was early 2000. And there was a presentation on transfer entropy. I had no background on that topic whatsoever. And it intrigued me, and it intrigued me sufficiently that I read up about it. I looked at Schreiber's paper, and then I introduced one of my former students, Ben Ruddle, uh, to it. And he is a very enterprising person, and he started working on it. And we went through long discussions in there, and I got more and more excited about how information theory may be tied to dynamical systems. I mean, that's something that I had not seen before. There were things like analogy to entropy maximization principles in there, but it more so from a thermodynamic entropy approaches. There are definitely links to information theory and entropy. And the more we worked, I developed a little bit more of a hunch, and I had no proof in there. And it was that there is something to information flow, much like we talk about flow of mass and momentum and energy from different components. And if information flow could potentially anchor aspects of dynamical system that we don't understand. And so through various works since then, um, it has become, I'm more convinced that there is something more fundamental in that space than we are able to put our arms around it. And uh, with time, it became even more clear to me that information theory, while using statistical measures, is not a statistical quantity. Or I shouldn't say information theory, information itself, while we characterize it through statistical measures, is not a statistical quantity. Much like when we write physical equations using differential or partial differential equations, we are essentially characterizing something using a math. It's the same way with statistics. We are characterizing something, some stuff called information using probability or probability-based approaches. So that's what I'm after, step by step as to how this idea can move forward. There have been physics literature basically saying information is a physical stuff, which is consistent with what my hunch was, and then it was a little bit more corroborated through what's going on in in physics realm. And there was a paper called "Information is Physical," which I had not known at that time. And there is recently a paper I came across, and I haven't read it, so I'm just going to mention it. And they're trying to speculate if information is a fifth state of matter. Now, this is far-fetched, but nevertheless, it's intriguing. So much like we talk about solid, liquid, gases, plasma, is information a fifth state of matter? And probably it's better thought about it from the perspective of quantum mechanics, because I think eventually everything we do with quantum mechanics is with PDFs. And so it's easier to think about it that way. In terms of translating those ideas to classical mechanics, not so trivial. But that's my intriguing journey, and it has been absolutely fantastic to be working with some very, very bright students. I think they have helped me think rather than I haven't contributed so much to how they think. So it's been great. Ben Ruddle, Alison Goodwell, Pishi Jiang, Leila, and several other students that I have currently. So I'll keep it that way. This is how I got there, and maybe Hoshin, you have a different path.
Thanks, Praveet. That's great. I was just reflecting on when you said fifth state of matter. I tend to see it the other way around. Matter is a state of information, which has certain properties.
Yeah,
So
at some
that could be
point,
an
yeah.
interesting discussion.
Yeah, no, fair enough.
Because if you think about information as coming as information is inherently a something discrete, which depends on a process of representation, and all processes of representation are fundamentally discrete. So this is part of the problem we run into. And I was looking up, um, uh, the fact that information is physical, and it has a very strong connection to the fact that particles are um, quantities that what's the word I'm looking for? Uh, I'm drawing a blank at the moment, but I was looking up on the web for the last few months the the thing that makes particles particles. And you get into this thing if you've got a field, I forget what it's called now. Um, Higgs field, I'm sorry, the Higgs field, and then a particle is a property of something that comes out of a Higgs field. And when you look at it from that perspective, and I think Landauer had stuff to say about this, is that information is not separate from mass and energy. So anyway, just a reflection of your thing about whether um, information is a state of matter or matter is a state of information.
Yeah, no.
Yeah. I think, Joe, you were asking more broadly about what the problems we chose to study and why do we choose those, and how did that take us to information theory? Did I characterize that correctly?
Yeah, that's right. And thank you, Praveen. That was great.
In my case, it was pretty much determined by the fact that when I got to graduate school, Surush was working on modeling of hydrological systems, and his PhD thesis had a lot to do with um, saying we shouldn't use mean squared error, we got to use maximum likelihood as a mechanism. And that had to do with understanding the fact that different data points have different degrees of reliability associated with them. And as we started looking at that bigger problem, part of what I did for my dissertation was sort of characterize the fact that we had two parts of the problem. There was the model structure, the representation that we chose. Um, there was the metric that we used to tune that model. And then there was the optimization mechanism that we used to adjust the model. Um, and we had this picture which Suresh still uses when he gives his presentations, which is kind of like this pie thing. Actually, I think he uses something which looks more like a yin yang, but it's kind of like this model metric optimization or search. And while a lot of focus in the early days was on the metric and how we had to search it in order to optimize the model, uh, it became sort of very clear to me that the real problem was the model, which is where the information was stored, and then the metric was the way of characterizing whether you had extracted that information from the data, and then the search method was whether you'd done a good job. How did you optimally extract that? And the early problem that we had to deal with was based on a paper by Johnson and Pilgrim. JNP was it 1976, I believe, which not sure how many of you have seen, but it's a really interesting paper. I think it was WRR. And they reported a study where they spent 2 years trying to calibrate their model to the data and were unsuccessful at coming to a best solution. And two things about that paper stood out for me. One was that they actually reported a failure. Hardly anybody ever does that, right? And I always thought that was great because reporting your failures is what helps other people figure out what are interesting problems to study. Um, and um, um, and then of course it raised the question was why? Why were they on it? And at that point, right now looking back at it, it seems almost laughable that that was a concern, that we really didn't understand why it was that people were having trouble calibrating their models. Um, so, that sort of got me started on the journey. And so that's why we worked on global optimization early in the day. Um, the thing about the metrics kept coming back because it was very clear that when your model was imperfect, your metric imposed an inductive bias on how the model would extract information from the data. And so at a very early stage, it sort of concerned me that we were not focusing on the model and the model structure error. And so a lot of stuff I tried to do, like multi-criteria, was based on the idea that a single criteria is not capable of extracting all of the information from the data, particularly and then balance. Do I want to fit peaks? Do I want to fit low flows? Do I want to fit rising them? Do I want to fit falling them better? All this kind of stuff. And so multi-criteria was sort of an early stage, and then that led to the idea of diagnostics. What kind of criteria? Well, criteria that emphasize different kinds of information. Um, and then what took me to information theory was
Just a quick question on that,
sure.
Because Yang and I were discussing similar things, and uh, I think he was wondering, and I was wondering it definitely as well, if you subscribe to like the Bevan notion of like behavioral models as well.
Mhm.
So
Mhm.
you don't think that there is I mean, there's basically a large group of models that work more or less equally well. Do you think that's the case?
Sure. So, so you're talking, to me, the problem you're talking about is one of dimensionality, which is whenever you expand from some lower dimension to a higher dimension to construct your representation and then back down, that inherently there is no unique way of doing this, right? You can rotate and transform this in an infinite number of ways, and you will get equivalent representation. You can get equivalent representations that are behaviorally identical, right? So I think the focus on behavioral was okay, but it was based on the concept that somehow you had this internal latent representation that made sense. It had some particular interpretation that you cared about. And so to me, the issue is not is behavioral is not sufficient. It's also structural. It's interpretable. Which particular transformation or rotation of the latent space is the one that you prefer because it has meaning to you. And then the other problem is that what the metric measures is behavior. It doesn't measure structure. All right. In some sense, what it measures is, are you matching observed behaviors to simulated behaviors? Um, but it's always felt to me like the model and the metric were dual aspects of the same problem. So that as you developed your model, you should be adapting and adjusting your metric to reflect the capabilities of the model. And that's what sort of comes up under generative adversarial networks nowadays. That's effectively what they do. They train both the metric and the model at the same time.
I think Sharush had a bunch of papers on that too, as well, right? Like he was doing some iterative thing, trying to estimate the weights of the observations.
So Sarush's approach was to say that the individual observations had a different variance depending on their magnitude, and then to try to learn the structure of the variance as a function of the magnitude. And then Jasper did some work on that too. Although what Sarush did was he proposed that you use a very fixed architecture, which is basically a power law relationship. And then what Jasper did later on was say, no, you could extract that. Correct me if I'm wrong, Jasper. You could kind of learn the nature of that relationship directly from the data. And Manuel's not here right now, but he's just he's going to be graduating um, next week, and he's done work on variational LSTMs, where he's effectively learning the form of the likelihood function as a machine learning problem, right? So in some sense, that's similar to generative adversarial. So he's basically learning a mixture of distributions, which does what Timothy is interested in, which is basically which minimizes the entropy of the residuals. Yeah. So sort of different ways of looking at the same thing. Um, but what brought me to information theory had more to do with diagnostics. And so the question was, information theory supposedly tells us how much information's in the data. And Wei Gong came along, and then Gray came along, and I was interested in the problem of how much information's in the model. And it was, is there a way of uh, is there a way of establishing that you have transferred all of the information from the data to the model? And then is there a way of characterizing that information? So this gets back to what Praveen said earlier, which is that information is not a purely statistical quantity. And arguably, that's what Kolmogorov also said, right? Information in Kolmogorov's sense, is an algorithmic quantity. So there's Shannon information and then there's Kolmogorov information. And now I think that, and what I'm trying to say is there's something called representational information, which has to do with your, not the complexity or the length, the number of bits, but has to do with a particular representational architecture that you choose, of which there are infinite, but you put an inductive bias which says I want one which has a particular kind of meaning.
Yeah, and I think adding to that, Les Soshin, there is physical information, and that's what I'm trying to articulate, that that's a physical quantity, and therefore we should treat it as.
Oh, the other thing I'll say, Joe, is just quickly, because I don't want to dominate this, is what I've noticed is in terms of problems, there's sort of two directions that people tend to go. One is they learn something, they understand something, and then they try to see how far they can take that. And that's kind of what I call the forward problem. But arguably, what's always interested me was I learned something and I went, why? And I tried to go backwards. And it's that backward journey towards what's causing this. Where did this come from? Where did this come from? That I think led me to information theory.
Yeah, thanks for that.
Jasper, did you have something to add to that?
Yeah. So I missed the first few minutes, but I guess, Joe, your question is what brought people to information theory? Do I understand it correctly?
Yeah, more or less. Yeah.
Yeah, so I most of you probably know, but I took 6 years off between 2015 and 2021 because I was dissatisfied with the research I was doing. In a sense that I felt I wasn't challenging myself. And I thought if I work so many hours, then at least I want to be able to tell myself that, I did something that at least I challenged myself. And I felt that a lot of, and I'll just speak for myself, okay? But I felt that what I was doing is I was just taking concepts and putting things together. And then most of my colleagues, when I was a PhD student, we would have lots of alcoholic beverages during the week. So you meet a lot of people, and most of my friends, they were professors in physics, mathematics, and then I would share some papers with them what I was working on, and they immediately would put out, they put their finger on the weak spot. They say, "Oh, this, this assumption, this assumption, this assumption," and so this is a long time ago. And then I would study their work, and I would notice, oh my, they have 50 citations in their whole lives so far. But the papers they published are very rigorous, very difficult maybe to read. So I was like, this is so weird. You have people working on the surface, they're scratching the surface, they get hundreds of citations. And then when you do something really rigorous, there are like 10 people in the world that understand what you're doing. But those people win a Nobel Prize ultimately, right? So like there's this really interesting contradiction. So you work on the surface, you get some data set, you analyze it with the faulty method because you don't know enough about methods. And then I talk to these people and they immediately say, oh, this is wrong, this is not right, you can do this, are you aware of this? That intrigued me from an early age. So then, walking around in this area for a little bit, and then publishing some papers, I just felt this is so superficial in essence. And then I also found that at several important, and Hoshin mentioned one of them, and that's why I wanted to respond to, related to this global optimization trend, this Pilgrim paper. Because I would argue that, and now I'm not saying that to be mean or anyway, but I would argue that a lot of times in applied fields, direction is taken in the literature because of a lack of knowledge. Because if Pilgrim the reason that went wrong at that point, the reason they couldn't solve that problem is they probably didn't use the right ODE solver. If they had used a proper numerical solver for their hydrological model, they would have noticed that that response surface was actually smooth, wouldn't have numerous local minima. So it's a lack of knowledge, a lack of mathematical knowledge, how to solve differential equations properly. That leads to these fixed step Euler integration methods that introduce a lot of issues with hydrological models. So that in some, and I see this all the time in the applied literature, and that is exactly the thing that led me to, you know, taking that long break to really re-educate myself, and that's what led me to information theory ultimately, because that is really one really important foundational field. Like you can't go deeper than that essentially in describing information in a time series or so. So that's the so that is how I look at it. So if I look at the literature, then oftentimes I can come up with a few other examples where like I think we produce a lot of interesting ideas in hydrology, but they lack fundamental underpinning. And that's why if you bring that to a statistician, a mathematician, a physicist, they read it, they say, hey, nice idea, but now we have to start working. Like, and that's what I miss a little bit. And that's so beautiful about information theory, that you actually, it's like, it's Lego, essentially. When you start playing with Lego, that's like the basic foundational pieces of almost everything. So it's a common language that we can use. And yeah, so I had that completely independently because I didn't really follow the literature for a number of years. I was reviewing papers, but it's not that I was really keeping up, and then COVID happened. So that is how I look at it. So I'm really looking forward to, because there's some papers have appeared about hydrological education, and some people argued that is it important to learn mathematics, statistics, and physics? And some people say, no, not too much of that. Whereas I would argue the complete opposite. I think it's crucial, absolutely crucial. Have a really strong foundational basis in those fields, then you'll notice it takes a lot of time, but then what comes out is just, you know, the benefits of that, the quality of your ideas. It's for most of us, it's a limiting factor, right? And I would argue that Einstein didn't have that as a limiting factor. Newton didn't have that as a limiting factor either. And I know these are absolute exceptions. Richard Feynman, they can just walk outside, go for a hike, they see something, a rainbow, they see a wildfire, and they can immediately, because of their foundational knowledge, they can turn an observation into a differential equation, they can solve it, they can tie it to something else. These very deep penetrating insights. And I think information theory helps with this as well. Plus, I think it helps us understand why machine learning is better than physically based models. We're missing something. Praveen and I talked about this yesterday. I think we more or less agree on, I think, what is missing in the physics-based models. But I think that's what machine learning, that's why it's so interesting. It's all coming together.
It's funny that you mentioned the artifacts of the optimization surface being due to kind of numerical issues, because I was kind of looking at that recently too. Specifically, all these papers on equifinality have these plots that are like 2D projections of like 15-dimensional surfaces. And I mean, based on my very limited initial experimentation, like if you actually look at the entire 15-dimensional manifold, it actually looks smooth. It's just because, people, it's just kind of a failure to visualize it properly that might be creating this equifinality problem.
Yeah, so what was,
I'm sure the numerical issues have a say as well, but yeah.
So, but what's always interesting, because I always worked on groundwater problems, surface hydrology. Then I worked at the lab in Los Alamos for 5 years, where there was a lot of groundwater hydrology. And they would always say, why are you guys using global optimization methods in surface hydrology? Because we always had a discussion in groundwater, and then the conclusion, yeah, groundwater is so well behaved, the physics is so well described, that's why you can use gradient descent. But that's because groundwater models use proper numerical solvers. If we had done that in surface hydrology, we wouldn't have run into problems. In fact, I talked to Praveen yesterday. I developed some new machine learning ideas in hydrology, and I can now calibrate a surface hydrological model using gradient descent in like 15 steps. In 15 to 20 function evaluations, I can estimate 10 parameters just using, so it's going like instantly. The training goes so fast now without any numerical differentiation, not needed anymore. So that shows that if we had done that 30, 40 years ago, and I think if people had a better mathematical upbringing, we would have been there years ago, much, much, much faster. So that's just one example. There's numerous other examples. So I think this is essential material for every undergraduate students, is information theory, just the statistics, like really core courses that they are familiar with these things. Because most students, when I teach my classes, I always tell them how I felt. And that was like, you're reading a paper, you don't really understand it. You're trying to understand it, but you don't have the time to understand it. And the first thing you do is there a piece of software? No, there's no software. Okay, then let's go to the next best thing, right? So imagine that you can read papers and that you can understand everything at the foundational level, right? That means you're unlimited. There's nothing in research that says, okay, you can do this. So anyway, I think I made my point.
Yeah, we should definitely talk more about that, because I was actually going to write a proposal for a Stanford undergrad to take on like this equifinality issue. And I wasn't thinking about the numerics so much, although I was thinking about it a little bit. But yeah, maybe we can steal your idea and loop you in a little bit too.
Because it's dangerous. The last point I make is that when you talk to people in machine learning, so in my class, I derive everything, the training, all the back propagation and all that. So the students really understand what's going on. Most people working on machine learning today, they know how to run a toolbox. If you ask them like what it is you're doing, what is back propagation, what's a gradient, what's an Hessian, what's a Jacobian, how does that work? They have no idea. And that scares me. Yeah, I mean, it's okay. There will always be people that apply and people that understand more of that's always true. But I think if we do a better job in educating, but I must also say, I mean, some of you know my latest papers. All the reviewers always say, remove all the math, put it in an appendix. We don't want to see it. We want to read your paper as a magazine article. And I keep telling them, no, I want that mathematics to be in the paper. I want people to be confronted with it, because if you no longer confront people with their limitations, you move all that out, then people need to be confronted. And at one point they think, oh, it must be important, let's invest energy. But it's also with the editors nowadays, I think, that they're looking for papers with all the theory hidden away in an appendix. That's also not good. Readability.
Sorry, I got to take a little bit of exception there, Jasper, in the sense that it's clear that there are at least two parts to theory, and mathematics is one of them. The other part is the ideation and the concepts. And arguably, Einstein was successful because he had both an interesting idea and the mathematical chops to be able to express it and then, demonstrate it. But arguably, math can be essentially dead if it doesn't contain any ideation in it. So part of what we're struggling with the publishing process and the communication process is we're using mathematics as a language to help express ideas, and we're trying to communicate ideas, and then mathematics becomes part of the language that we're using to express the ideas. So we shouldn't ignore the fact that underlying, I think it was Einstein who basically himself said that that there's something. What was it? The term he used, something like um, to the extent that reality is represented by mathematics, or to the extent that mathematics. There's some interesting comment that he made. that mathematics is just a language which is an incomplete description of reality. Yeah.
I agree with you. I'm just concerned that if I open
Yeah.
WR that of like 1980, 1990, I saw much more theory. I don't see as
Sure.
much theory anymore nowadays. And I
Sure.
think it's really important for people to
You
be
just
confronted with theory
I'm
because
just
that's good.
I'm
Yeah,
I'm just pushing back that theory doesn't necessarily mean mathematics. That's all I'm saying.
sure,
Yeah.
sure. But I think editors nowadays they're looking more for, and that's I think it's all related to each other. We also, I think all of us, we see the importance of information theory, all these concepts. And but I see, yeah, if we want to have more people, you know, if we want to promote this, it's important, I think, that we think about these things.
Sure.
Presentation, marketing, publication, everything included. Yeah.
Just a question for Joe, though. When you're using the term equifinality, um, are you using the term in the sense that Bevan uses it or some other sense? Because I'm going to argue that Bevan's term equifinality was more confusing than anything. Um,
Yeah, I don't know if I have a good definition off the top of my head, but maybe the problem that I was trying to look at is if there are actually multiple local minima. Uh,
okay. So, so if you look at a linear system of equations, the basic rule that we learned when we learned linear system of equations was that if you've got p parameters, you need p equations, uh, p independent equations. You need to form a complete basis. And you had to be able to invert that system in order to uniquely determine the parameters of that system, right? Um, uh, the problem we run into is you take a model which has, let's say, 10 parameters, and then I try to identify the values of those 10 parameters with a single metric, which means that you're projecting from a 10-dimensional space down to a one-dimensional space. Now, if you can drive that metric to zero, there may be a single solution. And if the basis is not complete, there won't be a single solution. You'll get a space or a line of solutions. Right. Yeah. But here's the problem. Your model is never accurate, is never a complete representation of the data. And so when you plot the metric, you're going to get an infinite number of solutions that give you the same value of the metric. Yeah. They lie on a contour of some kind. And in fact, you can get many flat regions. And part of the problem is that you're projecting from RD down to R1 where you should actually be using, if you've got a d-dimensional space, you should be using d metrics. Yeah. Each metric is targeted towards that one particular parameter or combined. Yeah. So this is part of the problem, is that we're doing lossy compression when we go down to one-dimensional space. By construction, we're not preserving all of the information that we need. So that's part of my problem with that definition of equifinality. Is, to me, equifinality is inherent anytime you go up in dimension, and then, well, anytime you go down in dimension, is what I was trying to say over here, is that you can rotate and transform this representation in infinite number of ways to give you exactly the same value of the metric.
right. I mean, I'm sure that's true for, neural networks, but it's less clear. I mean, there's no real rotation that you can do for like HPV calibration, for example.
No, but you can take multiple models. In principle, you could write multiple models that are different versions of HBV internally, right? Yeah. Um, so every time we build a model, we effectively build a different representation. Uh, And in principle, you should be able to translate from one to the other. Yeah.
Oh, right. Yeah. I mean, I
Yeah.
totally agree that there would be, tons of different models that are equifinal in some other way. But I was mostly,
Yeah.
I mean, that's a great point. But I was mostly talking about like within one model, the parameter sets
Sure.
causing
So,
equifinality. But yeah.
so then the question becomes, um, even if you take care of all the numerical artifacts, Jasper, you still might have a problem with multi-local minima, which has nothing to do with numerical artifacts. It just has to do with the dimensionality that you and the transformations and the nonlinearities in your model.
Yeah, based on my initial experiments, I'm not sure if that's true. Like, at least for like our most popular conceptual models.
So I think you're right. It's not true in general for machine learning because of this thing called the Koopman operator. And the idea of the Koopman operator is that you can take any dynamical system and you can transform or project it into a space where all of the dynamics are linear. I believe groundwater, some people in groundwater use this concept. I was reading about it recently.
Hmm.
So if you project up to a sufficiently high dimensional space, I mean, what are they called in surrogate vector machines? Kernels, right? And I remember reading somewhere that kernels are effectively nonlinear projections. Sorry, infinite dimensional projections, nonlinear infinite dimensional projections. So presumably, if you project up to a high enough dimensional space, you can transform your problem from uh, into one where all of the dynamics are linear. That's my understanding of what the Koopman operator is about. Which means in that space, you principally should have a convex optimization problem or something like it. But it's easy enough to see that you can take a nonlinear problem and you can project it down to a lower dimensional space and it can go from being convex to non-convex. Just by
Sorry, Hoshin. Keep
yeah,
going. I don't want to. So yeah,
that was it.
basically, the way I see it is that so in theory, with the perfect model, right? Maximum likelihood theory, generalized least squares will give you converges to the data generating process parameters. That's all been shown by statisticians. That's all standard stuff. Same with Bayesian inference, right? It all works beautifully. But the moment you have misspecification, that's when you run into issues. What Ocean's been working on diagnostics and all that. That's where you need multiple metrics. I always found because you get trade-offs in your model because of structural errors, right? So depending on the metric you choose, you no longer converge to one and the same set of parameters. Always what I found weak in the equifinality concept is that, and I think when I was in Arizona, Hoshin, you were teaching this, and I thought it was very powerful that equifinality, that's only a result. If you use a single metric, right? And two different simulations give the same value for that metric, but when you actually plot those simulations, they're different. So I always found there's something. I try to avoid that term in my paper essentially. Every single time I see that word, I prefer the word uncertainty than over equifinality. But yeah, I think it's basically equifinality result that you're not extracting all the information that's in the data. It's basically a result of a poor way of yeah, using one metric. If you use two, three, four, or five, you will notice that there's actually there are differences. So yeah.
Anytime you got two errors and you can increase one while reducing the other, you're going to have equifinality.
Yeah, it's an underdetermined system essentially, right?
Right.
That's what
Yeah.
you learn in Gauss elimination. Get a consistent solution, you need at least a number of equations equal to a number of variables. So it's yeah, you're essentially boiling down to one equation with 10 unknowns. And if you would use 10 different metrics, you would notice that yeah, then you start to see differences.
But Joe, you were saying you and Yang were having some conversation that motivated this. We might have gone a little far from that. Could you bring us back to that?
I can't really remember the exact conversation that Yang and I had, but we were talking about maybe the different kind of thought processes behind
Hmm.
equifinality because Yang and I, were right or we took a little bit of a break, but we will eventually write a kind of a review on how to evaluate well, I don't know. Am I allowed to say what we're about to do, Yang?
Yeah, I think it's good. Yeah,
Yeah.
so sorry for my background noise. With some construction going on, but yeah, basically we are trying to review the method for testing a hydrological model for making predictions for a specific event, which we have no knowledge about. And we are looking at the different options. So basically, we consider this uh, problem as model selection. So there are many models you can use for making predictions for the future. And we want to understand whether model selection is a way of like reducing ego finality. So because we have a number of choice and we finally will use one or a group of models for making predictions. Yeah, so that's why we talk about equifinality in that sense. Do we have another better terms to describe the problem? So for model selection without knowing the ground truth. So,
So you're saying that you have multiple models and you have to select between them
yeah, or
in
specific.
regards to some future event for which you don't yet have data.
Yeah.
Okay. Interesting.
To me, I like to think of like a huge space of all the possible models that we can create. And, you know, uh, we don't want to like shrink that circle such that it's like biased and it doesn't include the ground truth model, but we do want to shrink the circle a bit. And, wait, like having observations only can shrink the circle too far if you believe in so far if you believe in equifinality. Um, but maybe there are other ways without having observations that you can shrink the space of possible models even further.
So I guess that's consistent with the Bayesian perspective, which is that you retain all possible models that explain everything you've seen so far. So you don't just focus in on one, and that as you collect data, you would progressively narrow that down. But it doesn't have to be data. It could even be conceptual inductive biases that you would use, right?
Yeah, you can use all the models, right? Instead of trying to eliminate all but one. After you do some training, I assume, and some of these metrics we propose in this misspecification papers will give you an idea about the distance to the ground truth. If you compute those divergence, so you may be able to use that as a means to weigh the models essentially based on their distance to the unknown data generating process, which I think is an interesting application of those metrics. So if you compute your sensitivity matrix and your variability matrix at your maximum likelihood solution or so,
So
then
This is consistent with the idea that information is something that helps you choose between multiple options,
Yeah,
right? You start with all the possible options that could explain that are consistent with what you know right now, and then anything that's information in that context is only if it helps you to reduce, to select, to sub-select from that set. Yeah.
yeah, and maybe if we're talking about prediction under change, maybe you don't want to go down to just one model.
Right.
Maybe you want to keep the whole ensemble, even though the model gets a low weight for an historic period or up to today, given that the system is changing itself, it may not be smart to throw that model out, but just to keep it in your ensemble. I think that gives you the best protection.
Yeah, but the point is that we have finite number of observations, and these observations, can be bad sometimes. So we want to go beyond the observations, looking at, what if a model fails metamorphic analysis? You can yop those models out of your ensemble. What if this model is, like, for some reason always relying on like the correlation between temperature and stream flow instead of actually using precipitation? You can remove those models.
Yeah.
Yeah.
So yeah, but you can do that without having any observations, right? So that's just another post-processing step or something before you actually use the model to check for the internal consistencies or yeah, which is interesting because we usually don't really do that.
Well, it's worth reflecting on the fact that this is where theory, uh, predates practice, right? Because practice in modeling was always determined by the fact that we had very limited computational power. So we've always built deterministic models, lossy models, and thrown away all of the information about uncertainty because otherwise use we couldn't do computation.
That's right. That's why we're also so long. We've been stuck for so long on these squared residuals, Gaussian ideas, because you can do a lot of stuff analytical, and that was dates, before we had computers. But nowadays, you can, with computing, we can relax a lot of that. Yeah.
I'm going to speak up for Praveen. He said something in the chat that he wants to focus a bit on the grand challenges of info theory. And I'll just say that quickly. I mean, it's certainly relevant to some of the latest advances in machine learning. Now, if you look at what's coming out of Meta and other research groups, they use a transformer, which, right, it works for practical reasons. But then on top of that, things are tending to become much more, a lot of the breakthroughs they're making tend to be theoretical in terms of use of differential equations or information theory or statistics. It all seems to be coming back, which is a good thing to see.
Can I make a trite comment, which is the value of theory is it tells you where to look. Unfortunately, it can also blind you and cause you to not look in places. So that's why you need observations.
Sure. But yeah, and to Jasper's point about a core curriculum, right? It needs to be part of the curriculum. It's part of developing your chops. The challenge is always knowing, exactly which technical or which theory or which technical advance thing is going to be relevant to the next major advance. And we'll just say like transfer entropy is an example. Like, will transfer entropy unlock the secrets of the universe? I certainly don't know, but it's worth testing. But that's just the challenge for a curriculum. But I think I agree with Jasper that it definitely deserves a place somewhere in the curriculum as a sort of general very general paradigm, which was needed.
Well, if you listen to Ken Stanley, he will point out very, very strongly that um, progress is uh, major progress is made um, by people putting things together that were not previously thought to be even related to the problem that they were trying to solve. And so he has a, a bone to pick with um, gradient descent type optimization on problems, which he says it's good for solving. It's good for the what I call the forward moving problem, where you're trying to move forward and you understand something and you do a local optimization. But I think the example he likes to point out is that vacuum tubes were not invented with computers in mind.
So talking about the grand challenges then of information theory, maybe I say something really dumb now, but I'm still struggling with the fact that is there an implicit assumption in information theory that we're working with the correct model?
I don't think so. But well, I think the problem with that is you still have to go back and ask what is information and how do you characterize information? Because the moment you characterize information using some formal mechanism, Gödel's law comes into play. And that formal characterization completely constrains what you can do as you move forward. So you have to be constantly keeping your sights on the assumptions that you're making.
Because that is, I think, to answer Praveen's question about what are one challenge, of course, is for us to be able to use information theory in a way that people see its practical value. That is a demonstration of that. But that's not really related to theory or so. That's just marketing in large part.
So,
And,
so if you don't mind, let me bring up the thing that's been bothering me, okay? And maybe you guys have some perspective on it. The moment I choose what to measure, I have limited my window on reality. So I'm making very, very strong assumptions that the things that I choose to measure are the things that are going to provide me with the information I need in order to address my problem, right? So I'm going to use slightly different language, but hopefully this makes sense. When I choose what to measure, I'm quantizing the universe. I'm breaking it up into bits, into things that I focus on and things that I don't focus on. And then that fundamentally then determines, what I can do as I move forward. And if you look at I'm not sure I connect this very well, but let me just take one moment to try to say this. If you look at the architecture of a neural network, and I'm going to take this from the Kolmogorov-Arnold network perspective. Kolmogorov basically, the Arnold network basically says something like this. Says you got two variables. I'm going to just stay with two input variables and one output variable. And they basically say that you can approximate the relationship between x1, x2, and z by that theorem, right? And basically the theorem says is you have to expand from a two-dimensional space to from a d-dimensional space to a 2D plus one-dimensional space, and then back down to one. And that there are only two operations that you have to perform: addition at the nodes and nonlinear transformations along the links. You guys remember the Kolmogorov-Arnold theorem? I can write out the equation if you need to, but that's basically what it says, right? Where x and z are on the unit cube. That's the other thing. They have to be on the unit cube. So two observations. One thing is that, first of all, what they don't point out is that you're actually taking x and you're allocating it along different paths. So you're taking multiple copies of your input and you're doing independent transformations of those multiple copies. So you're projecting from a lower dimensional space to a higher dimensional space. And that's a kind of a discretization process. You're saying, I'm going to make 5 copies. It's not a continuous number of copies. I'm going to make 5 copies in particular, in this particular case. And then each copy, I'm going to do a nonlinear transform on. And then I'm going to do an addition operation. So there's actually 3 kinds of operations over here. There's this operation, which is what I call a decomposition operation. Then there's a transform operation. And then there's a composition operation. And then you do that many times. And so strictly speaking, there's only 3 kinds of operations. There's decomposition, transformation, and composition. And as far as I can tell, our modeling strategies are all based on this, right? Whether it's machine learning or any physically based modeling approach. It's just very obvious in machine learning. This is what you're doing.
But Hossein, well, sorry to interrupt, but
yeah.
In the machine learning, right, you do first do the composition and then the transfer, right? At the node level. You first do aggregation and then you do transfer.
No, if you've got inputs, right, you first
I mean,
you
you can do it the other way around.
I'm going to set multiple copies to different places. Yeah, you could do transform first. I mean, in principle, you could do these in any order you wanted.
To make
right?
sure,
I mean,
yeah. Okay.
Yeah. But if you look at a standard machine learning algorithm, you take X, you send multiple copies, and then you multiply it by a weight, right?
Yeah. And then,
okay. And then you take these from different things and you add them together.
Yeah.
And then you pass it through a rectified linear unit or some nonlinear transformation, right?
Yes.
So you can do these in any order you want, but all I'm saying is those are the 3 fundamental operations.
Yeah.
And then the question I was asking myself, what is a transformation? And as far as I can tell, a transformation is just a nonlinear scaling. So in a standard machine learning model, you do linear scaling, and in a CAN architecture, you do a nonlinear scale. Right?
Yeah.
And a nonlinear scaling can be thought of as a linear transformation in a higher dimension. Yeah. Which is why going to higher dimensions can help. Yeah. So the interesting thing about nonlinear transformations is, by the way, is related to diffusion modeling. I can take a Gaussian distribution on X, and I can do a nonlinear transformation on X, which converts it into bimodal or any other form of distribution. That's what diffusion modeling is all about, or generative modeling is all about. If you do it invertibly, you can, yeah. So as far as I can tell, there's no fundamental difference between regular machine learning architectures and Kolmogorov-Arnold networks. It's just the implementation. here we're using linear scaling, and then we do these nonlinear transformations afterwards, but there's nothing stopping us doing nonlinear scaling and then doing addition. Anyway, the problem I'm grappling with is I'm struggling with trying to understand what is actually happening as we go layer by layer through this network. It seems to be something like this, as far as I can tell. So we go from two-dimensional space, we do some kind of transformation, scaling transformation, and we project it into a different dimensional space. And then we do some kind of a dot product operation or whatever, matching operation, and then we keep doing sequences of these. Not sure if that's making any sense, but that's kind of what I've been grappling with recently.
So for those working with PyTorch and all that, the implementation that Hoshin described first, is that the implementation you can do that you first do the transfer and then the aggregation, the summation? Is that possible in PyTorch?
I assume so. I've never done it, but it's pretty flexible.
Okay.
I mean, it's like saying, should I work with X or should I work with log of X or EXP of X or X squared, right? When you do a polynomial composition, you're basically saying, I'm going to work with X, X squared, X cubed, X fourth, and so on. That's a polynomial approach. You can take a basis function approach and you can take X and you can break it into different frequencies.
Yeah.
I mean, fundamentally, this is what we do. Yeah.
The chain rule is more difficult. That's why they probably don't, because now you're going to get an individual differential for each transfer, whereas normally transfer at the node applies where you get one Jacobian of the transformation, and now you have for each individual input variable, you have a separate Jacobian, which you can still work out with the chain rule, but is mathematically a little bit more cumbersome. But
Well,
it's
the original one was considered cumbersome until somebody wrote the code to do it for you.
Yeah.
Go ahead, Dan.
Thanks. I have a question. And like, looking at, different orderings of operations or, different architectures, to me, it seems these are ways of unshackling the flexibility of a model for extracting information. And so, there's plenty of work with people trying to couple these with like physical concepts or laws. That's one thing that applies constraints. But I guess when I think of these approaches, I think, okay, well, this is just a very, very flexible model. The most flexible model that I can imagine using. And so when I finally got around to testing out the neural hydrology package, it just really occurred to me that, and I'm really curious about, I think Hoshin, at the very beginning, you mentioned the somebody's work.
Manuel?
Manuel, that's right.
Yeah.
And what were you saying, like approximating the component distributions for the mixture?
Yeah, so what he's doing is he's using an LSTM to output things which can then be interpreted as the means and standard or the parameters of distributions,
Okay.
which are then composed together to generate a probabilistic output. And you can do that with an LSTM, for example, and then you get an LSTM which predicts the probability of an observation rather than just predicting a deterministic value. Yeah.
Okay, yeah. So that's really interesting to me, because it kind of comes around to my exploration with this, where the default objective function or loss is the NSE in neural hydrology. And so if you have a large sample, and you you have I don't know, several hundred time series in your training data, and you apply an NSE loss function, you are, the first thing I noticed was that, yes, and it was pointed out in one of the early papers, if you run multiple simulations with different random initial weights, you're going to get very different answers. And looking at how different the answers are was really interesting to me. So, I just thought that reducing and using this particular loss function, of course, there are an infinite number of ways that we can arrive at the same NSE given initial weights and given like different structures and everything. And so that to me was okay. Well, at least for now, I'm just not that interested in what the architecture does, because it's much more flexible than the information in our a lot of time series, because it's so noisy, and the observations are relatively small compared to like just the capacity of that model, of that approach in general. So yeah.
Sorry, can you decompose that for me? I know one has to do with the choice of metric NSC, but the other thing had to do with how you arrive at the solution. Or was there something else I missed?
Yeah, I guess I just like when I run multiple simulations and I randomize the initial, I give it an initial seed, a random initial seed.
Yeah.
That was in one of the early papers for this, that ended up building this this library, or this software package. They point out that running multiple simulations, giving a unique random seed gives different random initial weights, and you end up with very different simulations, like outputs for, if you're testing on however many 10%, you will get very different results. And then using an ensemble, provides I guess a more accurate, like it reduces the I guess sensitivity to outliers on an individual level, because the training loss is the NSE on the training sample. So of course there are an infinite number of ways to arrive at like something very close to in the neighborhood of a small NSE, global NSE, or I guess optimal NSE, not small, close to one.
Well, you're talking about the neural ODE package?
Neural hydrology.
Oh, the neural hydrology package, sorry. Freddie's package.
Yeah.
Right. I mean, I guess my first question is it clear to you that you can get with any particular metric, in principle, you could get multiple solutions?
Yes.
And there are two reasons for that. One is that they may be, multiple reasons. One is you've got model error, right? The second is you have noise. And then the third is that they may be, your model may be overspecified. Sorry, or I guess underspecified. Not sure what the right language is, Jasper. But in principle, so you could get an NSC surface in 2 dimensions that looks like that, and that would be well behaved, right? But you could also get an NSC surface in 2 dimensions that looks like that, where this is the minimum, right? So if you start from different parts in the parameter space, you could converge to different combinations of parameters, right? That's your second possibility. And then the third possibility is that this region is so flat in high dimensional space that effectively any point over here, right? And all that that's telling you is that the data is not sufficient to constrain your model to a unique set of parameters. So all of those models would have to be retained based on that metric.
Yeah, so Hoshin, quickly, so this is primarily an issue if you have this flat response surface where you start working with numerical derivatives. If you
No,
work
you
with,
can you
if
you
you
can have
work with,
flat. Sorry,
yeah,
go
yeah,
ahead.
no, sure,
You
whether
can get
it's
flat
flat or
response
not, it is
surfaces even if you
independent of
don't
the
have
derivative.
problems with the derivatives. Yeah.
No, but what I'm trying to say is that if you have a flat response surface, because that's also with neural network training going on. In
Yeah.
large parts of the network, basically the gradient is really close to zero. And then when you get really close in a small range of weights and biases, you suddenly get a really steep gradient. And so this issue, of course, with the shape of the response surface has nothing to do with the derivatives. But my experience is that even if you have a flat response surface, once you have exact derivatives, it will still be able to find that absolute minimum. The
Sure.
issue is that if you do that numerically, these derivatives vanish, and that's when you get along that line indeed. And because we usually do it numerically, that's one of the issues, is that we do not find that small area, because there is still a gradient, but
No,
it's just,
Jasper, if your covariance matrix has what's it called? Condition number. Um, what's the term I'm looking for? If you have several eigenvalues that are zero,
yeah.
you will get to surface like this regardless of whether you have numerical
Yeah,
artifacts.
I agree.
Yeah.
So the response surface, the way it looks, is independent of the derivatives. That's just the way it is, right?
That's right.
But
Yeah. Then you can
yeah,
add noise on top of it with the numerical artifacts. Yeah.
so yeah, and those numerical artifacts become important when you have a flat response surface. And my experience is
Yes.
with an analytic noise-free gradient, you still be able to find that area reasonably well.
Yeah, and Duan showed that in his SCE paper,
So
that if you did little local calculations, you got little pits right in the surface. And the shuffle complex evolution helped to avoid those pits, yeah,
I
by
think
doing a kind of smoothing.
sorry. Where I was going with this was with this NSC is that I think what troubles me is that I mean this what you wrote there
Hmm.
you wrote Gaussian. Well, we can within all these random initializations, we'll just have kind of arbitrary hedging of certain models, right? So it has the ability to hedge and make worse predictions in certain areas too, right? And that's this coming back to this idea of equifinality. But then after going through Jasper's most recent paper, I know there are other model heads in this library, but it just seems to me that there must be a better way to go through, rather than this default loss where you can't
Well,
hedge.
think of your loss. Okay, I'm just going to call it L as being some average or some sum on a function of E1 plus some function of En, right? That's sort of our typical loss structure. It happens for mean squared error, we choose squared, but you can choose absolute, you can choose any transformation. You can transform the input variables before calculating the error. You can do anything you want, but that's your loss function. Does that make sense, Dan? Right? Yeah. So, um, um, so this is one choice, and then what we're saying, this also reflects this idea of independence, right? So we're saying each error is independent of each other error. There's a bunch of assumptions that we're making. Yeah. So if this is squared, it corresponds to Gaussian, but you can transform this to any other distribution you want with that scaling transformation that I was talking about, right? So this is, I mean, okay, this is like Kolmogorov-Arnold theorem again. You've got nonlinear transformations and you've got summations. Same basic idea.
note
Yeah, I
that you
mean,
cannot write the NSC this way, yeah, and the KG.
Pardon?
You cannot write
Sorry.
the NSC and KG this way.
Well, yeah, you can write NSE is equal to 1 minus L, we use squared, divided by sigma O squared. That's NSE, right?
But you cannot write it the way you did it now in the topic where you have a total loss and an individual loss. Because you divide the denominator, sigma sin O squared, requires knowledge of all the data points. That's why you cannot, strictly speaking, write it out. Same with kg.
Well, you can write it as 1 minus, and then this is a sum of individual terms, right?
Yeah, but that's, again, for the individual terms, you assume knowledge in the denominator here of a variable that's determined from all your data.
Yes, absolutely.
So you
Yeah.
cannot, strictly speaking, that's not a limitation of NSE of kg. Kg
No,
is the same way
no.
because the correlation
Right.
coefficient requires all the data.
Yeah, this is just a scaling or a weight, right?
Yeah. But
And
so,
you're
and
just,
that, yeah,
yeah. And all you're saying here is that you're giving the same weight to every one of the
yeah,
every one of the transformed errors. That's all that's doing.
I know, but that requires all the data. That's why you cannot, strictly speaking, write it out as a sum of individual losses.
Yeah, but the basic point is you calculate this after the fact. You only need this term in order to do the optimization. Right. I mean, people like to report mean squared error and Nash efficiency, but they're one-to-one related. You just minimize on mean squared error, and then afterwards you can calculate Nash efficiency. The only reason you need this in the neural hydrology package is because you're using a different value for every catchment. Yeah. Anyway, where I was trying to go with this, Dan, is you could take mean squared error and you can decompose it that way, right? 1 over n sum of ET squared. But you can also write it as delta mu squared plus delta sigma squared plus 2 sigma s sigma o 1 minus rho, right? That was the mean squared error decomposition. And now instead of it decomposing into n terms, you're decomposing into 3 terms, right? And presumably you could write any number of decompositions of the mean squared error where you have 5 terms or 7 terms or whatever, right? And then what I'm trying to point out is there's no reason that you have to use a squared transformation. So you can make this as flexible or complex as you want, right? You could take a whole bunch of e's, join them together, and then calculate a nonlinear transformation on them. Or you could take the original data, transform them, and then calculate the e's. I mean, there's just an infinite number of ways that you could try to project from the data space down to the metric space.
And you're saying this E is the most general function. It's not strictly a residual.
I'm saying
Could
that
be likelihood.
ET is observed T minus simulated T, right, over here. But I could make this F1 of observed T plus F plus, minus G of ST, right? That's one definition of E. Another definition of E could be some function of observed T divided by some function of ST. And more generally, E is just some function of OT and ST, right? I mean, you have complete flexibility in what you want to do as long as you preserve certain properties.
I agree with Hoshin. I just wanted to add that you can pick any function, but if it's not amenable to automatic differentiation, you're going to have.
Yes.
But Tim, most functions are. The funny thing is, I have 2 papers right now ongoing that are exactly about this. Then answering your question about the NSE, for instance, where I include M estimators in there. Because you can replace that squared loss or squared residual loss. You can replace that with an M estimator, which is more robust against outliers. So you get a general form You can generalize the form of the NSCs. You get a generalized form, and then one of them is the squared residual. But you can also replace this with the sum of absolute residuals. That's one. And the other thing is, for almost all the loss functions in hydrology, you don't need to use automatic differentiation. Okay. Anyway, maybe I should present that work.
Yeah.
You can do this all analytically.
I'll just raise a couple notable exceptions, like, if you wanted to compare distributions by computing the CDF, that involves a sort operation. So
Even then, so yeah,
Actually,
you can still
Tim,
do.
in our recent paper, we had a CDF function that's like differentiable. I guess that exists in Python.
Yeah, right. Okay. I mean, again, I want to be careful here, but there's various works around, and people have leaned for other certain tests over others based on what works well for automatic differentiation.
If you write out the chain rule, you'll see all the individual Jacobians, and then you'll see that almost in all cases, we can do it analytically. And that will speed up the training tremendously. Really, you avoid all those toolboxes you don't need to use because they slow things down.
I tried to write down, there may be some other rules there, but there's it's a very small set of rules that you have to obey.
We never did any discuss planning for next year's topics, but rather than derail, I'm just going to share an interesting.
Okay, right.
If you haven't seen it, it's pretty cool. From if you're familiar with Jan LeCun's work on JPA, sort of representation learning.
Sorry, something in the chat?
Yes.
Yeah, okay.
By the way, I'm taking notes about the paper that you have mentioned, so I'm gonna share that later. Yeah, sorry, Tim, for interrupting.
No, it's okay. I was just saying that I'd be happy to present on this paper next year.
Cool. Hmm.
By the way, Dan, I think you always are going to have to hedge. Like your initial point is always going to, have a large effect on your outcome, just because, I mean, unless you're in like an extremely low dimensional space or your loss is like convex, um, your loss landscape is convex, then yeah, I think the initial point will have a big influence.
Anyway, I'd like to thank all of you. I need to go, I need to teach, but it's wonderful to have a group of colleagues that you can talk to this way. Certainly for young students, right, to have access to colleagues that you can interact with, bounce ideas off. I remember when I was young, that was only possible when you went to meetings and you ran into colleagues and you talked to them. It was always very inspiring. So it's nice to talk to all of you on a regular basis via this medium. So that's the good thing of the internet, right? So I want to thank all of you. I have to go. I probably won't see you. I'm not sure if I go to AGU or not this year. It's been enough travel. It's my daughter's birthday, and she's getting at an age where she starts to have an opinion. And last week she suddenly mentioned, "Oh, you weren't there the last 2 years at my birthday," and so suddenly comes out at the blue on the way. Anyway, so I better be there this year. But anyway, thank you so much, and hope to see you all soon.
Yeah, good to see you, Jasper.
Thanks, Jasper.
Thanks, Eps.
So you took us on a journey, Joe. Any comments?
Yeah, I didn't really mean to do that. I just
No,
thought
no,
I'd
that's the
fill the
purpose
empty
of our.
space. But it took an hour and a half. Mm.
That's called a good question. Hmm.
I didn't get a chance to push back in time, but of course everyone's path is very different. In my undergrad, I have a very vivid memory of learning Maxwell's demon, learning about Maxwell's demon in thermodynamics, um, and at the time it really didn't have much of an impact, and it took more than 10 years to come back around to um, seeing it seeing its sort of general power. And so I think that's where my real interest in this comes in it. Um, yeah, so being exposed to that theory early on, it's a limitation of my own capacity to grasp it, but to get the motivation to dig into it later, um, how do you get that into curriculum? I don't think you can. It's my own limitation.
Yeah, you could say that about my experience with statistics and many topics of the undergraduate curriculum. Yeah. So I became a geologist.
Well, there's this idea in, I'm abstracting a little bit from Zen, which is uh, the power of a good question, right? So a koan in Zen is effectively a question which does not lend itself to an easy answer, or if an answer at all, right? And its purpose, as I understand it, is really just to lead you on a journey of discovery, right? So maybe part of the answer to Joe's question is find a good question. Find the question that wakes you up in the morning thinking about
That's the question.
it.
Thanks, Ocean. Thanks, Joe. See you
Cool.
guys.
All right, so I guess we won't meet again till after AGU or sometime in January, right?
Yeah,
Yeah.
mid-January. I think the session falls on January 14. I don't know if it's that too soon, but it's, I think, the week before. Yeah, the universities start opening again.
Yeah,
So,
I think we should not meet till at least the 14th. Yeah.
yeah.
Okay. Sounds good. Maybe people can report back on their questions.
Yeah, we can have an opening session on the 14th and we can start planning from there.
Okay.
Maybe that would be good to keep some time, like maybe once or twice a year to do some sort of this talk, like
Mhm.
throughout the year. Like every time a semester ends, or I don't know, something.
I
Yeah,
agree.
that's
I
a
would
good
say at
idea.
least 3, even 4 times a year, because sometimes it's more interesting to just talk about things that are bothering people, right? Yeah.
Well, this is when ideas are created, like during lunch or dinner, like just talking. It's not like after a presentation, usually it's just discussion. You start up with an idea and build up on it.
Sure. Sure. Yeah, for me, the question has been related to how does compression drive learning, right? And uh, I'll just say this now and we can pick up some other time, but it's very clear to me that you can do compression that leads you in a direction where you get something that's not interpretable at all. And that what we're trying to do is not just compression. Compression isn't just learning. Compression is uh, a, you're trying to do compression that leads to something that's interpretable, not just nuts. Because you know, if you take a course on compression, you'll see that there's lots of strategy used for compression that reduce the data to something that doesn't look like anything that you can understand. Right? Like video compression, which is allowing Zoom to happen right now. Yeah. You can't just examine the compressed elements and go, yo, now I have understanding. It's nothing like that at all. So anyway, see you guys in a month or 5 weeks. Yeah.
Yeah, thank you everyone for
Thank
this
you. Bye-bye.
discussion.
Okay.
Thank you.
Bye.
Bye.
Thanks, Leela and Antoine.
Bye.
Bye.
Thanks.